4.5. Describe the occurrence in superconductors below the critical temperature of a population of electron pairs unaffected by electrical resistance. So let's start on to what superconductivity is, and that's the second paragraph there. Superconductivity describes the state reached in a conductor when the resistance to electron movement in a conductor drops to zero. So electrons are in charge carriers in a metal. At room temperatures, from paragraph 1, the metallic bonds holding a conductor vibrates and interferes from itself and with the electron movement in the conductor. So the superconductivity is when it's got none of these effects. Along with the impurities, imperfections in the lattice itself, these three factors are responsible for resistance effects in a conductor. So to think about superconductivity as having none of these and it's having resistance of zero, it's quite phenomenal. However, there are two states, and you need to know these two states. There is a type 1 and a type 2 semiconductor. Looking at the diagram on the right hand side, you can see the visual diagram that shows of a superconductor. So changing the temperature will affect what is happening to the magnetic field between the superconductor. So if you're looking at the type 2, you're going to have the magnetic field going through the superconductor, and this is called quantum tunneling. Where in a type 1 superconductor, they go around the superconductor, which still holds it in position, however, it doesn't experience quantum tunneling. So what are the differences between type 1 and type 2? Research has shown there are two types of superconductors. For a number of pure metals, superconductivity occurs at temperatures from close to absolute zero and up to 23 Kelvin. Now this is extremely cold. This is looking at minus 273 degrees. Okay. From another group of conductors, ones that have been manufactured using alloys of metals and metal oxides, superconductivity type 2 has been demonstrated to high temperatures, so in the range of 120 Kelvin, which is still quite cold. However, it's moving closer to 0 degrees. So at temperatures below the critical temperature, lattice effects impeding electron movement changes dramatically from impeding to assisting electron flow. That assistance comes about by an effect that pairs of electrons and assists them to move freely from the conductor or through the conductor. So what are the two things here that you need to know is that when superconductors are below critical temperature, the electron pairs are unaffected by electrical resistance, and you've got two different types of superconductors at these states. You've got a type 1 and a type 2. And by visually in the diagram, type 2 experiences quantum tunneling, which locks the superconductor into position, while type 1 has the same effect, however, the magnetic field goes around the superconductor material.